WASP-76b. It is not strange because it is distant or obscure. It is strange because we can observe it clearly and still struggle to reconcile what it is doing with what planetary atmospheres are supposed to allow. Located roughly 640 light-years from Earth, this exoplanet belongs to a class known as ultra-hot Jupiters, gas giants orbiting so close to their stars that conventional models of weather, chemistry, and circulation begin to fail. WASP-76b completes a full orbit in just under 2 Earth days. Its year lasts approximately 1.8 days. That proximity exposes it to relentless stellar radiation far beyond anything experienced by planets in our solar system. The planet is tidally locked. One hemisphere permanently faces its star, while the opposite side remains in continuous darkness. This configuration produces an extreme thermal contrast. Observations indicate that the day side reaches temperatures around 2,400 degrees Celsius, hot enough to break molecular bonds and strip electrons from atoms. At these temperatures, common planetary materials do not behave as solids or even conventional gases. Metals that would normally exist only in foundries on Earth become atmospheric constituents. Spectroscopic studies using instruments such as the espresso spectrograph on the Very Large Telescope revealed something unprecedented. Iron, normally associated with planetary cores, was detected in gaseous form in the upper atmosphere of WASP-76b. The detection was not subtle. The absorption signatures were strong, structured, and persistent, indicating that iron was not a trace contaminant, but an active component of the planet's atmospheric chemistry. The most unsettling part came from how that iron behaved. Intense winds, measured at several kilometers per second, appear to transport vaporized iron from the permanently illuminated day side toward the cooler night side. As the gas crosses the terminator, the boundary between day and night, the temperature drops enough for the iron vapor to condense. Models suggest that it then falls back toward the planet as liquid metal precipitation. This is not a metaphor. On WASP-76b, the atmospheric cycle likely includes clouds of metal and rainfall composed of molten iron. What makes this phenomenon difficult to fully explain is not just the presence of iron, but the stability of the system. Atmospheric circulation under such extreme conditions should, in theory, be chaotic. Yet repeated observations show consistent spectral patterns, implying long-lived global wind structures capable of maintaining this metal transport cycle. Current models of atmospheric dynamics struggle to predict how such organized flows persist when exposed to constant stellar bombardment and extreme ionization. Further complicating matters, measurements indicate asymmetry in the iron distribution. The trailing hemisphere of the planet shows stronger iron signatures than the leading side. This suggests that the planet's atmospheric dynamics are not evenly balanced, and that unknown factors, possibly magnetic interactions with the host star, may be influencing how material moves across the planet. WASP-76b does not merely stretch our understanding of planetary weather. It challenges the boundaries between atmospheric science, plasma physics, and planetary formation theory. It is a world where metal behaves like rain, where days and nights exist in permanent opposition, and where physics appears to operate at the edge of its known limits. Scientists can describe what is happening there. Explaining why it remains stable is a far more difficult problem. KLT-9b. It occupies a category so extreme that its existence initially challenged basic assumptions about where planets can survive. Located roughly 670 light-years from Earth, this gas giant orbits a massive, intensely hot star classified near the boundary between A-type and B-type stars. Its host is far hotter than the Sun, radiating immense amounts of ultraviolet and visible energy. KLT-9b circles this star at such a close distance that a full orbit takes just under a day and a half. Its year lasts approximately 1.5 Earth days. By planetary standards, it is effectively skimming the stellar surface. This proximity produces temperatures unlike anything else observed on a confirmed planet. Measurements indicate dayside temperatures exceeding 4,000 degrees Celsius, with some models placing peak values closer to 4,600 degrees. That is hotter than the surface temperatures of many red dwarf stars. The distinction between planet and star begins to blur here, not metaphorically, but physically. Under these conditions, conventional atmospheric chemistry collapses. At such temperatures, molecules cannot remain intact. Water vapor, carbon compounds, and metal oxides are torn apart into individual atoms. Even those atoms do not remain neutral for long. Spectroscopic observations show signatures of ionized metals, including iron and titanium, stripped of electrons by the intense heat. KLT 9b's atmosphere behaves less like a planetary envelope and more like a low-density stellar plasma. The planet is also undergoing active atmospheric escape. Ultraviolet radiation from the host star heats the upper atmosphere to the point where hydrogen and other light elements reach escape velocity. Observations have revealed an extended envelope of gas trailing the planet, forming a comet-like tail that stretches tens of thousands of kilometers into space. This is not a subtle process. KLT 9b is losing mass continuously, shedding its atmosphere under relentless stellar irradiation. What makes KLT 9b particularly difficult to explain is not just how extreme it is, but how it persists at all. Standard models of planet formation suggest that gas giants form far from their stars, where temperatures are low enough for volatile materials to accumulate. For KLT 9b to exist in its current orbit, it must have migrated inward after formation, surviving an environment that should have stripped it apart long ago. How it avoided total atmospheric loss during this process remains an open question. Another unresolved issue lies in the planet's internal structure. Despite its extreme heating, KLT 9b maintains a gravitational hold on much of its atmosphere. This suggests either an unusually massive core or physical processes that slow atmospheric escape more effectively than current models predict. The balance between loss and retention is precarious, and scientists do not yet understand where that balance breaks. KLT 9b represents the upper boundary of what can be called a planet. It is hotter than stars, composed of disintegrating matter and actively dissolving into space. It does not behave like a world so much as a transient physical system, existing briefly in a state where planetary physics gives way to stellar processes. Explaining how it formed, how it survives, and how long it will continue to exist pushes current planetary science to its absolute limits. HD 189733b. It is one of the closest exoplanets ever studied in detail, located just over 60 light-years from Earth. At first glance, it appears deceptively familiar. Observations show a deep blue world, a color striking enough that it was once casually compared to Earth from a distance. But this resemblance is an illusion. HD 189733b is not a water world, not an ocean planet, and not remotely hospitable. Its appearance masks one of the most violent atmospheric environments ever observed. The planet is a gas giant slightly larger than Jupiter, orbiting its parent star at an extremely close distance. A full orbit takes just over 2 Earth days. Like many close-in gas giants, HD 189733b is tidally locked, meaning one side permanently faces the star while the other remains in darkness. This configuration drives extreme temperature gradients that fuel atmospheric motion on a scale difficult to model. The blue color of HD 189733b does not come from liquid water. Spectroscopic analysis has shown that the hue is produced by silicate particles suspended high in the atmosphere. These particles scatter blue light in a manner similar to how Earth's atmosphere scatters sunlight, but the material involved is fundamentally different. The particles are not ice or vapor. They are microscopic grains of silicate, essentially the building blocks of glass. Temperatures on the day side of HD 189733b exceed 900 degrees Celsius. At these temperatures, silicate materials can exist in molten or vaporized states. As material circulates through the atmosphere, it cools and condenses into fine glass-like particles. These particles form clouds, but they do not behave like anything seen on Earth. Wind speeds on HD 189733b are among the fastest ever measured on a planet. Data indicate winds exceeding 2 kilometers per second, roughly 5,000 to 5,400 miles per hour. These are supersonic flows, moving several times faster than the speed of sound in Earth's atmosphere. The planet's weather system is effectively a global-scale shock environment, driven by constant stellar heating and rapid rotation. In this environment, precipitation does occur, but not in any familiar form. Models suggest that condensed silicate particles fall through the atmosphere as molten glass rain. Because of the extreme wind speeds, this rain does not fall vertically. It is driven sideways, scouring the atmosphere in high-speed streams. The result is a constant barrage of glass particles moving laterally at thousands of miles per hour. What makes HD 189733b particularly unsettling is not just the violence of its weather, but how stable it appears to be. Despite the extreme winds, intense radiation, and continuous atmospheric cycling of solid material, the system maintains long-term consistency. Observations over many years show repeatable atmospheric signatures, suggesting that this glass-laced storm system is not transient, but persistent. HD 189733b challenges assumptions about what planetary atmospheres can endure. It demonstrates that clouds do not require water, rain does not require liquid, and weather does not require moderation. It is a world of constant abrasion, where the sky itself is a weapon. Scientists can observe its color, measure its winds, and identify its materials. What remains difficult to explain is how such an atmosphere organizes itself without tearing the planet's outer layers apart. 55 Cancri. Located a mere 41 light-years from Earth, it is a planet that defies both imagination and conventional planetary physics. Nicknamed the Diamond World, it belongs to a class of exoplanets known as super-Earths, worlds more massive than our own planet but smaller than gas giants. Despite its modest distance in cosmic terms, 55 Cancri presents conditions so extreme that it challenges every assumption about what a rocky planet can endure. This planet is roughly twice the radius of Earth, but carries 8 times the mass. That combination produces an extraordinary density, leading scientists to conclude that carbon is a dominant component of its interior. Advanced modeling of its composition suggests a landscape potentially rich in graphite and diamond. The very idea that a planet might be made largely of crystalline carbon stretches the limits of planetary chemistry, but observational data, including precise measurements of its mass and radius, support the hypothesis. Yet 55 Cancri is not merely valuable in composition, it is violent in environment. A year here lasts just 18 hours, placing the planet in a rapid orbit around its star. It is tidally locked, meaning one side faces the star constantly while the other remains in darkness. Dayside temperatures approach 2,400 degrees Celsius, hot enough to melt silicate rocks and create flowing lava lakes across its surface. Thermal radiation is relentless, ensuring that the illuminated hemisphere is a glowing, ever-changing inferno. Atmospheric conditions make survival, or even a theoretical visit, impossible. Pressure at the surface is estimated to be thousands of times greater than Earth's. This is not merely an annoyance or a matter of crushing weight. It is an environment that would instantly compress any human or probe into near-molecular flatness. Combined with surface temperatures capable of incinerating matter in moments, 55 Cancri is both literally and figuratively untouchable. Adding to the planet's strangeness, 55 Cancri exhibits extreme variability in thermal emissions across its surface, suggesting dynamic volcanic activity or possible lava flows interacting with a thin or patchy atmosphere. Observations from space telescopes reveal that one hemisphere appears hotter than expected, while the other is relatively cooler, indicating that heat is not evenly distributed despite its rapid rotation and close proximity to its star. The reasons for this imbalance remain speculative, but point to a planet that is geologically active in ways difficult to model. 55 Cancri embodies contradictions. Its name evokes wealth and beauty, a planet of diamonds beyond human reach. Its density implies a solid, crystalline elegance, yet it exists in a state of constant thermal and atmospheric violence. It is a world where the laws of geology and chemistry converge in extremes, where the very surface is at once priceless and utterly inhospitable. For scientists, it is a laboratory of high-pressure physics and carbon chemistry on a planetary scale. For humans, it is a reminder that the universe contains wonders that cannot be touched, bought, or tamed. In every sense, 55 Cancri E is a planet of paradox, dazzling in composition, lethal in environment, and utterly beyond human reach. The diamond world exists not as a resource, but as a demonstration that planetary science still struggles to explain the boundaries of what a planet can be. TRAPPIST 2b. It is a planet that redefines what it means to be dark. Located roughly 750 light-years from Earth, it has been classified as one of the darkest worlds ever observed. Its most striking feature is its albedo, or lack thereof. Less than 1% of the light that strikes the planet is reflected back into space. To put this in perspective, it absorbs more light than coal or any black pigment ever created on Earth. The result is a planetary surface so dark that it is, for all practical purposes, a world of pure shadow. TRAPPIST 2b orbits its star extremely closely, completing a revolution every 2.5 Earth days. This proximity exposes the planet to constant stellar radiation. Despite its capacity to absorb almost all incoming light, the surface temperature reaches nearly 980 degrees Celsius. It is an environment that is both scorching and invisible. On this world, the heat alone would be lethal. Any object or visitor would succumb to extreme thermal conditions before they could make sense of the darkness surrounding them. The visual paradox of TRAPPIST 2b is profound. It is a planet bathed in light, yet cloaked in absolute darkness. Observers note that the planet does not shine in reflection but emits faint radiative heat, giving it an eerie red glow detectable only through sensitive infrared imaging. This glow betrays the presence of intense thermal energy on a surface otherwise hidden in shadow. The combination of darkness and heat creates a planetary environment unlike any other known in the galaxy, a realm where the senses are simultaneously deprived and assaulted. The extreme light absorption is likely linked to the planet's atmospheric composition, though details remain speculative. Some models suggest the presence of exotic molecules capable of capturing almost all visible light. Others propose a surface covered in carbon-rich compounds, or iron soot, materials that act as near-perfect light traps. Regardless of the mechanism, the effect is consistent across observations, and TRAPPIST 2b continues to absorb more light than any other known exoplanet. This extraordinary darkness also has consequences for atmospheric dynamics. With minimal reflection of stellar energy, traditional models of planetary heating fail to fully account for wind patterns, temperature gradients, and heat redistribution. The planet's upper atmosphere is likely under extreme thermal stress, and continuous infrared observations indicate turbulent circulation on a planetary scale. Yet despite these extremes, the planet remains intact, maintaining its orbit and atmospheric characteristics over long periods. TRAPPIST 2b is an existential enigma. It exists as a physical body, yet defies our ability to see it in conventional light. It is a world where light is devoured, where heat is lethal, and where perception itself fails. For scientists, it represents a challenge to models of planetary albedo, composition, and thermal dynamics. For anyone imagining a visit, it is a place where darkness is tangible and the very concept of sight is meaningless. The darkest world forces a confrontation with extremes, extreme heat, extreme shadow, and extreme incomprehensibility. K2141b. It is a planet that pushes the limits of what a rocky world can endure. Situated roughly 202 light-years from Earth, it is often described as a magma planet, though that description only scratches the surface. This world orbits its host star at a breathtakingly close distance, completing a full revolution in just 6.7 hours. Such a rapid orbit exposes it to extraordinary stellar radiation, generating dayside temperatures around 3,000 degrees Celsius. At these levels, conventional rock does not merely melt, it vaporizes. The surface of K2141b is a literal ocean of molten rock. Lava lakes span the illuminated hemisphere, glowing with radiant heat and churning with constant motion. Observations suggest that the extreme heating drives a continuous cycle of evaporation. Rock and metal components from the molten surface enter the atmosphere as vapor, forming clouds composed entirely of mineral particles. These clouds behave unlike anything seen on Earth, or even on previously studied exoplanets. Supersonic winds exceeding several kilometers per second transport these mineral-laden clouds from the scorching day side toward the frigid night side. There, temperatures plummet to roughly minus 200 degrees Celsius. This rapid temperature drop causes the vaporized rock to condense back into solid form, producing precipitation unlike anything humanity has ever experienced. On K2141b, the rain is composed of rock, sometimes in fragments comparable in size to cars or small boulders. These rocks fall at immense speeds, driven by both gravity and high-velocity winds, creating a surface bombardment that would obliterate any object attempting to land. The extreme conditions do not stop at precipitation. The planet's tidal locking generates severe thermal gradients between the day and night hemispheres. These gradients fuel persistent, planet-spanning wind patterns capable of sustaining the rock's cycle indefinitely. Despite the constant violence of molten oceans, supersonic winds, and falling rocks, K2141b maintains a stable orbit and overall structure, defying expectations of planetary degradation under such stress. What makes K2141b particularly puzzling is the stability of its geological and atmospheric processes. The evaporation of rock on the day side, its transport through the atmosphere, and the solidification on the night side create a continuous loop that is consistent with observational data. Spectroscopy confirms the presence of vaporized silicates and metal compounds high in the atmosphere, moving from the day side to the night side in predictable patterns. Yet no model fully explains how such intense heat, high-velocity winds, and extreme material cycling can coexist without gradually stripping the planet apart. K2141b is a world where the rules of habitability, weather, and planetary physics are completely rewritten. Lava oceans and rock rain define a violent, yet systematic environment, a place where thermal extremes coexist with organized atmospheric motion. For scientists, it is a laboratory of high-temperature geology, atmospheric dynamics, and planetary evolution under conditions that seem almost impossible. For any hypothetical visitor, the planet offers no hope of survival. The magma would incinerate you instantly, and the supersonic rock rain would ensure nothing remains. K2141b exemplifies the extremes of planetary diversity, a world where the boundaries between solid, liquid, and atmospheric material blur, and where physics appears to operate at the edge of known limits. It is a reminder that the universe creates environments far more extreme than imagination alone can predict. GJ436b. It is a planet that defies conventional understanding of both temperature and material states. Located just 32 light-years from Earth, it is classified as a Neptune-like exoplanet, a world similar in size and composition to our own ice giant neighbors, yet existing in conditions that make any comparison deceptive. The planet orbits its host star at a close distance, completing a full revolution in only 2.6 Earth days. This proximity results in a surface temperature around 439 degrees Celsius, high enough to vaporize water under normal circumstances. Yet GJ436b is remarkable precisely because water behaves differently under its extreme gravity. The planet's mass is roughly 22 times that of Earth, producing surface gravity far stronger than Neptune's. Under these conditions, water is compressed into a dense solid known as Ice X. Unlike familiar ice on Earth, Ice X does not melt under intense heat. Instead, it remains solid while exposed to temperatures that would instantly boil ordinary water. The result is a planet covered in water ice that is simultaneously in a state of thermal combustion, a burning ice paradox. The physical consequences of standing on GJ436b are unsurvivable. The gravity alone would crush any object or visitor instantly, flattening structures and organic matter alike. At the same time, contact with the superheated Ice X surface would cause immediate thermal injury. The combination of extreme pressure and intense heat creates a planetary environment where conventional physics appears almost contradictory, yet the planet maintains stability in orbit and structure over time. GJ436b also exhibits a surprising atmospheric phenomenon. Observations using infrared spectroscopy reveal a faint halo of escaping hydrogen and helium, suggesting that despite its dense ice-covered interior, the outer layers of the atmosphere are slowly evaporating under stellar radiation. The process is gradual but continuous, giving the planet a subtle, glowing envelope that hints at the violent thermodynamic interactions taking place below. From a scientific perspective, GJ436b challenges multiple fields simultaneously. Planetary formation models struggle to explain how such a planet could maintain both a high-density, ice-rich interior and a stable, close orbit around its star. High-pressure physics, thermodynamics, and planetary geology intersect here in ways that remain only partially understood. Current models of water under extreme pressure predict the existence of ice X, but the combination of high surface temperature and stable ice is unique, making GJ436 be one of the strangest exoplanets known. In every sense, GJ436b represents a world of contradictions: solid yet hot, water yet unboiling, stable yet extreme. It is a place where gravity dominates, temperature threatens, and conventional rules of physics seem to bend. For scientists, it is a natural laboratory for studying high-pressure ice phases and the interplay between thermal energy and planetary structure. For any hypothetical traveler, it is a place that can never be touched, a frozen inferno that exists entirely outside the limits of human endurance. GJ436b is not just a Neptune-like planet. It is a burning ice world, a paradox suspended in the cosmos, and a stark reminder that nature can produce phenomena that defy ordinary comprehension. PSR B1257+12 system. It is a place where the very definition of a planet is challenged by death itself. Located roughly 2,300 light-years from Earth, these worlds orbit a pulsar, a stellar remnant born from a supernova explosion, the dense, rapidly spinning core of a star that once burned brightly. Unlike a conventional star, a pulsar emits no steady warmth, no nurturing light. Instead, it beams lethal radiation across the cosmos, spinning like a celestial lighthouse at hundreds of rotations per second. This is the realm of the so-called zombie worlds, planets that orbit not life-giving energy, but a dead star. These planets hold historical significance. They were the very first exoplanets ever confirmed, discovered in 1992 by astronomers Alexander Wolzin and Dale Frail. Yet what made them historically groundbreaking also makes them utterly uninhabitable. Unlike the gas giants or rocky worlds familiar in our solar system, the PSR B1257+12 planets exist in an environment defined entirely by extreme radiation and the absence of stellar warmth. Their discovery proved that planets could survive, at least in orbit, around the most hostile remnants of stellar death. The danger in this system is immediate and absolute. The pulsar emits concentrated beams of X-rays and gamma radiation capable of annihilating unshielded life within seconds. Any object entering the system is subject to intense ionizing radiation, which can strip electrons from atoms, destroy molecular bonds, and effectively microwave organic material at a cellular level. Unlike planets where temperature is the killer, here there is no surface you could touch to avoid danger. The hazard extends millions of miles in every direction. Survival in the PSR B1257+12 system is impossible without extreme shielding, and even then, exposure would rapidly become fatal. What makes these worlds scientifically fascinating is their persistence despite such hostile conditions. Pulsars are remnants of supernovae, and the formation of planets in the wake of such explosions was once thought improbable. The existence of the PSR B1257+12 planets demonstrates that planetary bodies can emerge or survive even in the aftermath of a cataclysmic stellar death. They orbit with precision, their gravitational stability maintained over millions of years, despite the relentless barrage of radiation from their central corpse. These zombie worlds are also extreme laboratories for astrophysics. Their very presence challenges models of planet formation, stellar evolution, and orbital mechanics. Observations indicate that their masses and orbital periods are consistent and measurable, yet they exist in an environment that should have stripped away their atmospheres and vaporized any volatile materials. The persistence of solid planetary bodies in a pulsar system remains an area of active research and speculation. The PSR B1257+12 system is a cosmic graveyard, a stark reminder that planets can exist in the unlikeliest and most lethal conditions. These zombie worlds orbit death itself, bathed not in light, but in radiation that kills without warning. For scientists, they provide invaluable insight into planetary survival under extreme circumstances. For any hypothetical traveler, they are a tomb where nothing living can endure. This system stands as one of the most haunting and unapproachable corners of the universe, a place where life cannot exist and death reigns unchallenged. J1407b. It is often referred to as Super Saturn, and it is a planet that redefines the concept of rings. Located approximately 434 light-years from Earth, it is a gas giant roughly 20 times the mass of Jupiter. Its orbit around its host star takes roughly 10 Earth years, placing it at a relatively stable distance. Yet the planet itself dominates attention not for its mass or orbit, but for the extraordinary system of rings that encircle it. These rings are on a scale that dwarfs anything in our solar system, stretching hundreds of times beyond the radius of Saturn's familiar bands. If J1407b were placed in our night sky, its rings would extend far beyond the apparent size of the full moon, creating a celestial spectacle that borders on incomprehensible. Observations suggest that the ring system is composed of countless fragments of ice, rock, and dust, ranging from microscopic particles to moon-sized bodies. The density and scale of the rings make them unique. Their structure is so massive and intricate that the planet and its rings behave more like a miniature solar system than a conventional planetary body. The danger of J1407b is as extreme as its beauty. Gravitational forces around the rings are intense and chaotic. Any object venturing too close, whether natural or artificial, faces the threat of collisions with moons, asteroids, or dense dust streams. Even spacecraft navigating millions of miles from the planet could encounter catastrophic impacts. The system functions like a celestial meat grinder, pulverizing objects within its path. The density of material within the rings produces gravitational interactions that can accelerate debris to enormous speeds, effectively turning the environment into a high-velocity obstacle course on a planetary scale. The formation of J1407b's rings is itself a subject of intense study. Some models suggest that the rings are the remnants of shattered moons or material captured during the planet's formation. Others propose that they are temporary structures, destined to coalesce into moons over millions of years. Regardless of their origin, the ring's stability over the observed period is remarkable, maintaining structure despite the immense gravitational stresses imposed by the massive planet at their center. Spectroscopic analysis and photometric monitoring have revealed gaps in the ring system, likely carved by embedded exoplanets. These gaps, akin to Saturn's divisions, suggest active gravitational sculpting, adding further complexity to an already extreme environment. The sheer size of the rings, combined with the presence of debris large enough to act as moons, makes J1407b a dynamic and potentially dangerous environment where planetary and subplanetary objects interact in a chaotic yet structured manner. J1407b challenges our understanding of planetary ring systems. It exists on a scale that pushes beyond anything in the solar system, offering both a breathtaking spectacle and a deadly hazard. The planet is a testament to the extremes of celestial mechanics, where mass, gravity, and debris converge to create a structure both magnificent and perilous. For scientists, it is a laboratory in which to study the formation and dynamics of planetary rings. For any hypothetical visitor, it is a world where beauty and danger are inseparable, a planet whose grandeur is matched only by its lethal complexity. J1407b is more than a planet. It is a celestial anomaly, a super Saturn with rings that redefine scale, risk, and wonder, an environment where the physics of orbiting debris becomes both spectacular and deadly. PSO J318.5-22. It is the ultimate outlier among planets, a world that exists entirely on its own. Located roughly 75 light-years from Earth, it is classified as a rogue planet, a planetary mass object that drifts freely through interstellar space without orbiting any star. Unlike conventional planets, PSO J318.5-22 experiences no day or night, no seasons, and no fixed reference point for orientation. It is a world of eternal darkness, an island of matter floating through the void, completely unbound from the systems that give planets their familiar structure and rhythm. The origins of PSO J318.5-22 are likely violent and chaotic. Astronomers theorize that it was ejected from a parent solar system billions of years ago, possibly during a gravitational encounter with another planet or a passing star. Once ejected, it became a wanderer, left to drift silently through space for eons. Its solitary existence challenges traditional definitions of planetary behavior, forcing scientists to reconsider what it means to be a planet when orbital context is removed entirely. Despite its isolation, PSO J318.5-22 is not cold. Observations show that it still radiates heat from its formation, with surface temperatures around 800 degrees Celsius, hot enough to melt aluminum. This residual thermal energy makes the planet a faint, glowing object detectable in infrared light, a solitary beacon against the backdrop of interstellar darkness. Unlike planets warmed by the steady radiation of a host star, PSO J318.5-22's heat is internal, a remnant of gravitational contraction and formation processes preserved over billions of years. The experience of visiting such a world would be disorienting beyond comprehension. Without a star to provide orientation, conventional notions of up and down vanish. Any human presence would have no reliable reference frame, compounded by intense heat that would instantly prove fatal. There is no atmospheric weather system, no clouds, no rainfall, yet the planet remains dangerous simply by existing as a hot, isolated mass in an endless void. PSO J318.5-22 is also scientifically invaluable. As a young, free-floating planet, it offers a unique opportunity to study planetary atmospheres and thermal evolution without interference from a host star. Its spectrum has revealed details about clouds, temperature gradients, and chemical composition, providing a rare glimpse into planetary formation processes in isolation. The data collected challenge models of cooling, contraction, and chemical dynamics for planetary bodies outside conventional stellar systems. This lonely rogue exemplifies the extremes of planetary existence. It is a world unmoored, glowing yet dark, solitary yet scientifically illuminating. For scientists, it represents a natural laboratory where planetary formation and thermal evolution can be observed in isolation. For any hypothetical visitor, it is a realm of existential hazard, eternal darkness, extreme heat, and the absence of any reference frame. PSO J318.5-22 exists entirely on its own, a planet untethered, a wanderer in the vast, cold, and silent cosmos. It is the ultimate expression of isolation in the universe, a lonely rogue planet that drifts eternally, glowing from its birth yet unconnected to any star, a reminder that planetary existence is not always bound to light or life, and that the cosmos holds corners of solitude beyond human imagination.